What connects Pythagoras, modern jazz, the Mona Lisa, and sunflowers? The answer is beautiful, but irrational. You might find some aspect of mathematics beautiful, be it a graphical representation of an equation, a proof you find aesthetically pleasing, or simply an equation. In this video, we're going to look somewhere surprising where you might not know beauty lies. Irrational numbers. And we're going to ask the question, do we find irrationality beautiful? We're going to do so in 3 acts. Patterns and symmetries inextricably link music and mathematics. Leibniz, of calculus fame, stated, "Music is the pleasure the human mind experiences from counting without being aware that it is counting." In this act, we will explore how the study of music led to a revolution in mathematics, the discovery of irrational numbers. The Pythagorean brotherhood, famous for their right-angled triangle theorem, stumbled upon irrational numbers centuries ago. They were utterly convinced that all is number, seeing mathematics as the very language of the cosmos, almost like a religion. They noticed that harmonious sounds came from the vibrations with wavelengths linked by simple whole number ratios, 2 to 1 for the octave, 3 to 2 for the perfect fifth, which they thought was the most pleasant sounding interval, and 4 to 3 for the perfect fourth. They also found that the higher the number of these ratios, the more dissonant or unpleasant the sounds became. Then, a member of the brotherhood named Hippasus asked a seemingly innocent question. What's the ratio of the wavelength of the tone that perfectly splits the octave in two? He quickly proved that this number could not be written as the ratio of 2 whole numbers. This blew the Pythagorean worldview to pieces, so much so that they tragically killed Hippasus for this discovery. This interval, called the tritone, has an incredibly dramatic history in music. In the Middle Ages, it was even nicknamed the diabolus in musica, the devil in music. And there's a popular myth that the church banned this interval, however, it's apocryphal. I'll link a fascinating YouTube video in the description that dives into this. In modern jazz, the tritone is a secret weapon in reharmonization because the tritone chord shares vital qualitative tones with dominant chords, allowing for truly captivating melodies and progressions. But now back to numbers. Now that we've seen that there exist numbers that cannot be written as the ratio of whole numbers, the natural question is, how do we know if a number is irrational? In decimal form, rational numbers either stop or repeat, but it's not very practical. You need to observe an infinite digits to confirm rationality. Luckily, another representation, the continued fraction, makes this distinction crystal clear. A continued fraction shows a number as a series of fractions embedded within each other, and it has some truly mind-blowing properties. Crucially, a number is rational only if its continued fraction eventually ends, making it perfect for spotting irrational numbers. This representation also helps fill in the gaps of the rational numbers, a concept explored in my favorite video from last year's Summer of Math exposition called Reimagining the Reals, which I will link to in the description. Have you ever marveled at the intricate arrangement of florets within a sunflower? If you have a mathematical inclination, you might have even counted the spirals and discovered a fascinating pattern. But what connects the sunflower and these patterns to irrational numbers? Nature prioritizes efficiency, and the flowers that thrive are those that are optimally designed to gather energy from the sun. To maximize energy collection, florets must be distributed to maximize the surface area and minimize overlap. If a new floret were placed, say, a quarter of the way around a flower, the resulting pattern would only have 4 strands radiating outwards. Any rational number will exhibit a similar property. Therefore, to achieve both optimization goals, an irrational number should be used. Since there's always a whole number of florets, nature employs ratios that approximate irrational numbers. The more irrational, the better, and thus nature found the most irrational number possible. But what is this number? Continued fractions allow us to define a measure of irrationality, or how irrational a given number is. This definition is typically inverted to say how close a fraction is to an irrational number. Consider the continued fraction expansion for pi. A remarkably good approximation can be achieved with just the first few terms, 355 over 113, sufficient for almost any practical purpose. This stems from its continued fraction expansion, specifically the large number present in the sequence 3, 7, 15, 1, 293. The larger a number in one of these positions, the closer a rational number will be to the irrational it approximates.
Consequently, if we fill this entire sequence with the number 1, we obtain the most irrational number. Let's examine the fractions and see what emerges from this. The appearance of Fibonacci numbers in both the numerator and the denominator of these fractions is a direct result of how the continued fraction unfolds. This mathematical relationship explains why, for example, the florets in a sunflower exhibit Fibonacci numbering. They arrange themselves to maximize the solar energy absorption, naturally seeking out the most irrational number. This pursuit gives rise to the continued fraction that generates the Fibonacci sequence. The question then becomes, does this sequence of fractions converge to a limit? We will explore the answer to this question by examining aesthetics and art in Act 3. Let's try an interactive exercise. Take a sheet of paper and draw a few rectangles, aiming for the ideal shape, not too skinny, not too square, kind of like Goldilocks, just right. Now measure the longer side and divide it by the shorter side to get the aspect ratio. You'll likely find a value around 1.62. Where does this number come from? The precise value of this golden ratio can be found by observing that squaring the rectangle's short edge yields a similar but smaller golden rectangle embedded within the bigger rectangle. This observation provides the necessary insight to determine its value. Simply equate the aspect ratio of the smaller and bigger rectangles and solve the resulting quadratic equation. The golden ratio, half of 1 plus the square root of 5, is ubiquitous in art, appearing across millennia and cultures, from the Parthenon in ancient Athens, numerous works by Da Vinci, including the Mona Lisa, Hokusai's Great Wave, the Dutch Golden Age in Rembrandt, and even modern art in Mondrian. It's literally everywhere you look in art. And note one more thing. The golden ratio is also the unique number that is 1 away from its own reciprocal, a fact that we can use to determine its continued fraction. And we see that it is precisely the same as we found by studying the sunflower, and it answers the question of what is the limit of the most irrational continued fraction. The discovery of irrational numbers sent shockwaves to the ancient Greek mathematical world, challenging the prevailing belief that all numbers could be expressed as simple ratio of integers. They were initially viewed as an affront to the elegant and perfect order that mathematicians sought to find in the universe. This perceived irrationality was seen as anathema to the very beauty and logical consistency of mathematics. However, through the intervening centuries, as mathematical understanding deepened, it became increasingly clear that far from being flaws, irrational numbers are fundamental to the fabric of reality. They emerge repeatedly in nature, from the spiral patterns of sunflowers to the very geometry of the cosmos. Their presence is not merely incidental, but intrinsic to the harmonious proportions and organic growth observed in the natural world. Beyond nature, irrational numbers have also played a crucial role in the history of art, architecture, and aesthetics. The principles of design, from classical Greek temples to Renaissance masterpieces, often unknowingly incorporated ratios and proportions that are inherently irrational, contributing to their enduring visual appeal and perceived beauty. This recurring appearance in various domains, often in strikingly elegant and unexpected ways, has transformed the perception of irrational numbers. What was once seen as an imperfection is now recognized as a profound and beautiful truth, demonstrating the unexpected depth and complexity of mathematics and its intimate connection to the universe we inhabit.